Now we've looked at the effect of a magnetic field on a current carrying wire. It turns out that a current carrying wire also produces a magnetic field. It's kind of, and this is one of those things that was discovered by accident. There was this guy named Ørsted, Hans Christian Ørsted, who is credited with the discovery that a current generates a magnetic field. The legend has it that he was giving a public lecture, educating the public about various basic science principles, when he closed a circuit, and as he closed the circuit, he happened to look at a compass that was sitting nearby and saw that the compass needle was deflected from due north. And he investigated this, and as it turned out, he had discovered that these current-carrying wires were generating a magnetic field, which is kind of an interesting thing. So not only does charge, we know that charge creates an electric field, but moving charge actually is what causes magnetic fields. And that's even true of bar magnets, and we'll look more specifically at what's happening in bar magnets, I believe, next class. So if you have a wire, and this wire is carrying a current, you can figure out the direction of the magnetic field it generates by, guess what, the right-hand rule. So let's say we've got this wire, and it's coming straight up. Let's say it's carrying a current going upward, right? And the way you figure out the direction of the magnetic field is you put your thumb in the direction of the current, and then your fingers curl in the direction of the magnetic field. It turns out that if you have this wire, and forgive my drawing skills, in a plane that the wire passes through, the magnetic field will do this sort of swirly around in circles sort of thing around the wire. I'm no good at drawing in 3D, but you've got your wire, and then the magnetic field circles around it. Okay. Unfortunately, the batteries that I have are unable to generate a current strong enough for me to show you a compass needle deflecting as a result of just a straight wire. But it does happen. Ampere's law is the way that we quantify this magnetic field. And it's very similar, it's analogous to Gauss's law, which we learned back when we were talking about electricity. Remember, Gauss's law said that the E field, the integral of the E field with respect to the area was equal to the enclosed charge over epsilon naught. Ampere's law has a very similar formulation, but with Ampere's law, you take a surface, or you don't take a surface like you did with Gauss's law. You take a path, and it's as you go along this path, you're adding up parallel components of the B field. So if in calculus, that corresponds to what's called a path integral, where you integrate up the B field along with each little piece, each little length associated with your path. I think the book says something like sum of B parallel times L or something like that. But it's just taking the sum of each little B field, parallel B field component, and multiplying it to each little length segment, which is the integral of B as you go around this path. And Ampere's law says that's equal to mu naught, which is another constant, times the enclosed charge. Okay, and mu naught is called the permeability of free space. Epsilon naught was the permittivity of free space. Mu naught is the permeability of free space, and it's essentially mu naught is defined by this relationship right here. It is how much a given substance well, mu naught is for vacuum. Mu in general is how much a given substance is able to have a B field with respect to how much current there is around. But it's actually just specifically defined by this relationship. And it is fairly easy to remember. It's 4 pi, exactly 4 pi, times 10 to the minus 7th Tesla times meters per amp. As with most of these constants, it has goofy units. And we can figure out the B field of different current distributions based on Ampere's law. So let's take our straight wire, and for our surface, or for our path, we're going to take a circular path around the wire. And I already said the B field curls around the wire. So each component, each little piece of that B field, as you integrate it up, is in the direction of the path. And so instead of B dot dl, you just get B times that length. And the length around a circle, of course, is 2 pi r. Okay? And mu naught is mu naught, and the current enclosed is just whatever current is running through this wire. So the B field given off by a straight line current carrying wire is just mu naught I over 2 pi r, and the direction of that current is determined by the right-hand rule. So if I have my wire, say a current is going to the left, the field curls around it. So above the wire, the field would be pointing that way. If we get around to even with the wire, on the same height as the wire, the current would be pointing down. Underneath the wire, the current would be pointing this way, and over here, the current would be pointing upward. If I can get my finger in the screen, upward. Right. So let's consider what happens. Say we have two wires, and let's say they have current flowing in opposite directions. They're some distance apart. Let's think about the B field directly halfway between them. Pause the video for a second and figure out whether you think they would wind up adding to be double what it actually is, or whether they would subtract to become 0. And then when you unpause, you can see if you're right. So let's consider the right-hand rule. At that point, our current is going to the left here. The B field would be curling around this way, which means that at this point right here, the B field, I'll call this I1, well, it's the same current, but we'll call this wire 1, wire 2. And so I'll say the B field from 1 is pointing into the page. This guy, put our thumb to the left, and it curls around, which means that it is also pointing into the page at this point halfway between them. So the magnitude of the B field then would be double mu naught I over 2 pi r times 2, pi times, whatever the distance to that point is. If the currents were pointing in the same direction, then this one would cause a B field. You got a thumb pointing to the right, B field would be coming out of the page. This one would cause B field that is going into the page. And in this case, the B field at a point halfway between them would be 0. Now, another interesting result of the fact that current carrying wires generate a B field is that we already know that there is a magnetic force on a current carrying wire when it's in a B field. So if you have two wires next to each other, they exert some kind of force on each other. So let's consider this. First off, I want you to tell me whether you think the force for each, or not tell me, but pause the video, think about, and consider whether you think the force for each of these pairs, whether it would pull the wires together or push them further apart, whether it's going to be attractive or repulsive. So pause the video, think through that, and again, I'll work it out, and we'll see if you're right. If we consider we'll consider the ones that are pointing in the same direction because I have less stuff in my drawing here. Using the right-hand rule, the B field, because of this guy, up here would be pointing out of the page. That's the B field, this is the current. So, in order to determine the direction of the force, I put my hand in the direction of the current, curl my fingers in the direction of the B field, and that means that I can't contort my hand far enough, but the force on this wire would be going downwards. Meanwhile, from this top wire, the current's going to the right, we curl our fingers this way, and we've got a B field that points into the page at this wire. That's our B field over here, and our right-hand rule tells us that current cross B field gives us an upward force. And so in this case, wires with current going in the same direction, causes the wires to be attracted to one another. Whereas, I'll let you work through it on your own, but the opposite result occurs when the currents are in opposite directions. If the currents are in opposite directions, the wires will repel one another.